So, we will continue our discussion on the quark model. So, yesterday we discussed the grouping of mesons like pions under what is called the isospin. So, we said that we can consider pions as made of quarks and antiquarks and think about an isospin symmetry or isospin grouping under which U quark and a D quark belongs to isospin equal to half. So, I equal to half with U having I 3 equal to plus half and I 3 of U half U is plus half and I 3 of D quark is minus half. And similarly, we can think about the antiquark isospin half group D bar and U bar, and we said we will put a minus sign in whenever the wave function of U bar is considered. This will give you I 3 equal to plus half for the D bar quark and I 3 equal to minus 1 by 2 for the U bar quark. With this, we worked out that pi plus is actually a combination of U and D bar, and pi 0 when you actually get from the pion wave function thought of as isospin 1 and isospin 3 1 by plus 1, then we can actually use a step down operator to get the wave function corresponding to pi 0, and then that is what we did in yesterday, and we got 1 over 2 d bar minus u bar. The minus sign is because of the minus sign associated with u bar in the I 3 equal to half multiplet, and pi minus is again going to be D and U bar, only one such combination possible. So, this first one is our I 3 equal to plus 1, second one is I 3 equal to 0, and third one is I 3 equal to minus 1, all belonging to I equal to 1. This is what we discussed yesterday, and now we said we can also think about other mesons like kaons. In that case, what we do is we will have to consider the fact that U D, let me write that again, belongs to an I equal to half group, and yes, the strange quark S quark belongs to an I equal to 0 group, and similarly D bar U bar minus belongs to an I equal to half, and S bar belongs to an I equal to 0 group. So, with this U, D and S bar, for example, we can consider U S bar combination. This will have an isospin half because S has and S bar has isospin equal to 0, U has isospin equal to half. So, the only possible result and isospin of the combination is half, and I 3 similarly is plus half. So, we have I equal to half, I3 equal to plus half for the combination combined U S bar system as well. We associate this, or we identify this as the K plus meson, and from the other member of the quark doublet U isospin doublet UD, we have a DS bar, which is again I equal to half, but I3 equal to minus half, because D has isospin third component equal to minus half. And this, if you look at the electric charge, is it is a neutral particle, we denote that as K0. If you look at the mass of this, you see that experimentally they are have the same mass. We will come to some mass relations as we progress in quark model. Okay, so this is one thing. But then you also have a anti-quark D bar and U bar combination and S quark. So, with that again you can make U bar S, or let me take, since we are talking about the isospin half I3 equal to half first plus half first, let me take D bar S. So, now electric charge of D bar S combination is also neutral. So, I should be denoting this also as a neutral particle with a 0 there in the place of charge. But then this is different from K0, it is actually the antiparticle of K0. So, if you look at the quark content, it is clear that D goes to its antiparticle, S bar goes to its antiparticle. We said that antiparticle is a relative concept in some sense. So, together ds bar goes to its antiparticle. So, K0 goes to its antiparticle if you take this change, and this is again I equal to I3 equal to plus half system, and similarly you can have a K minus with U bar S, and you can put a minus sign because U bar is always there is a minus sign associated with U bar wave function. So, I3 equal to minus half belonging to an isospin doublet. So, if you look at again K minus, it is the antiparticle of K plus, because U has gone to U bar, S bar has gone to S. So, in a similar fashion we can actually think about other mesons also. So, there are many mesons which were discovered over the years, and all of them can be understood in terms of their quark contents, and we can apply the isospin symmetry properties the way we have done to all of them. Only thing is, now you have to consider the isospin. Along with this one, you have to also consider the C quark, B quark, C quark and B quark essentially. T quark, top quark does not really form bound states, we discussed that. So, basically considering the isospin of C quark equal to 0, B quark equal to 0 and S quark equal to 0, and an isospin of U quark is plus half with along with the D quark, we can work out the isospin of any of the mesons and also different combinations which will combine together to give isospin multiplet of any mesons. In exactly similar way, we can also look at the baryons, which are now made of only quarks, not antiquarks. So, for example, if you look at proton, you can see that if you look at U, then U quark and a D quark, then you will have a proton, and if you work out the isospin, then you will see that U quark has an isospin third component is equal to plus half, another U quark. So, together they will have an isospin combination of plus 1, and then you have a D quark which has an isospin third component minus half. So, together they have an isospin third component plus half, and you will see that you can actually work it out to get both proton and neutron belonging to one isospin group with I equal to plus half and I 3 equal to plus half for proton and I 3 equal to minus half for the neutron. Similarly, for other baryons, we can look at the isospin grouping. And in fact, if you are interested, a complete list of all the non-mesons up to today is available. Look at the particle data group, which actually compiles all this information from various different experiments and keeps it in one place for our easy reference. The URL of the particle data group or PDG is given here. So, you can take a look at that, then you will see that different mesons, what their other properties, the charges are, what their quark content is, what their isospin is, what their other quantum numbers are, and other properties are when they decay, what they do decay into, etc. So, a lot of information including what we have discussed here and many more information that we could not discuss in here are also there. So, please take a look at it. Underlying this isospin, we kept saying that there is isospin symmetry. At some point I said that there is some isospin symmetry, and then we can group these particles under the symmetry. What is the symmetry? The symmetry is basically this. And in fact, the whole thing originated from the fact that from the observation that neutrons and protons, although are electrically different and then will be behaving differently under electromagnetic interactions, because proton has charge plus and neutron has no charge, electrical charge. Although they behave differently under electromagnetic interactions, they behave the same way under the strong interactions. This was one observation that people made. Now, this then said that okay, in some sense they can be thought of as two different states of a single kind of an entity called nucleon as far as strong interactions are concerned. So, we can actually think about proton and neutron belonging to a nucleon, two states of a nucleon. In a sense, this is similar to the spin up and spin down states of an electron. If you forget about the spin part, okay, spin splitting, etc., or the magnetic interactions of including the spin, then electron, whether it has an up type, it has a spin orientation in the up direction with respect to some quantization direction, or down direction, opposite or along to the quantization direction. It behaves the same way for all purposes except for some special cases, except in some special cases like magnetic interactions, etc. So, now it is this analogy that we can take again here, and then this additional quantum number that will distinguish the nucleon is called the isospin, and we can make a statement that the strong interaction, since it does not distinguish between p and n, it is symmetric under isospin transformations. The sense that if you make a transformation from one state to another, which differs in isospin states, it is not going to make any difference as far as the strong interactions are concerned. This observation led to is the underlying thing that brings out the concept of isospin symmetry. And in the same way, we can actually talk about U quark and a D quark and then say that the strong interaction does not really distinguish between the U quark and D quark. And whenever there is a symmetry in particle physics, okay, or especially in physics in general, in physics, we try to associate that symmetry with some groups. It is an easy mathematical way of understanding symmetry. For example, rotation can be understood through what is called a special orthogonal group. Rotation in 3 dimension can be understood with the help of special orthogonal group of dimension 2, SO3. And the symmetry that is associated with the isospin is the symmetry group of SU2. What is SU2? SU2 is basically the following. If you take an element of SU2, any member of SU2, this member is unitary. If you take that member and the Hermitian conjugate of that member, say for example, in a matrix representation, you take a matrix, complex matrix, the Hermitian conjugate of the same matrix, and then that is going to be equal to the multiplication, the product of these two is going to be equal to 1. They are called unitary unitary matrices. So, the members of SU2 are unitary. Okay. In matrix representation, it is unitary matrix, they are unitary matrices. And special unitary is what the SU stands for, and the special here means that the determinant of the member element is equal to +1. You can show that the determinant of any unitary matrix is going to be plus or minus 1, and if you take only those with determinant equal to +1, then you will get the special unitary group. So, this is the symmetry group of isospin symmetry. And so, as we said, if you take Pn or Ud, they belong to a doublet of Pn or U and D. They belong to the doublet of SU2 isospin, and the strong interaction do not distinguish between the members of a particular multiplet, whether it is P or N does not know, U or D you cannot distinguish under in strong interaction. So, let me write that here for you. Strong interaction do not distinguish P from N. Or U from D. In fact, if you take a particular multiplet, it cannot distinguish one member from the other under SU3, under the strong interaction. Okay. This is actually similar to the case as we said, that the spin case, or the other way of saying is that another example is if you take a charged particle, electromagnetic interaction of charged particles. If a particular particle, say A has charge +1 and some other particle B has charge +1, their interaction, electromagnetic interaction, will be exactly the same with something else. Okay, if you take some background electric field, put a charged particle of charge +1 and another particle with charge +1, say under electromagnetic interaction, a particle A with charge +1 unit, I mean, and another particle with charge +1 unit behave in a similar fashion, which means that if you take A, put it in an electric field, and take B and then put it in the same electric field, they will experience exactly the same kind of force. Okay? So, this is not a strange thing, and then this means that there is a particular quality or quantity, quantum mechanical, or I mean property, which called charge, electric charge, and then that is the only thing which will distinguish the particle, nothing else as such. Similarly, there has to be something which actually is associated with the strong interaction. We call this the charge, strong charge, or the strong color charge, and that is the only thing to distinguish this particle, and then it is not the electric charge, say there, that will distinguish this thing. So, as far as that is concerned, then a U quark and a D quark behave in a similar fashion. We will come to the color charges later. Now, there is another way of grouping these quarks, which is called a flavor symmetry. Okay. Which says that if you take a U quark, a D quark and an S quarks, you can put them in a particular group. Okay. And this flavor symmetry, I mean the transformations within this is not going to make any difference as far as the strong interactions are concerned. With this, we can associate the symmetry group of SU3. Now, in a similar way, we can also take U bar, D bar and S bar and then put it under SU3. And this is called a triplet under SU3. Similarly, this is a U bar, S bar, D bar is a triplet under SU3. Now, when we combine these to make quarks, if you take a triplet, let me denote the triplet by 3, and an anti-quark triplet by 3 bar, under the SU3 we can understand this as a combination of an 8 and a 1. The objects that you will get, the result of this combination will actually can be classified under a group of 8 and 1 standing alone. What do I mean by this? This is something which we just now earlier said. Think about the spin half object, which is a doublet. In a spin half object multiplet, you have spin up or spin third component of the spin as plus half or minus half. There are two members. So, that is why it is a doublet. And take another spin half, combine them, you will get one spin 1 particle which belongs to which is actually a triplet. So, this is spin half cross half, another way of writing it. A spin here in the first case we are writing it as 2 cross 2 equal to 3, which means that 3 plus 1, okay, which means we are denoting this by the multiplets, number of members in a particular group, and second way of writing it is basically denoting it by the spins. Spin half is a doublet. So, spin half cross spin half will give you a spin 1 and a spin 0 in case. Okay. So, spin 1 has 3 projections, plus 1, minus 1 and 0. There are 3 values, plus 1, minus 1 and 0. In the case of spin 0, there is only one such as thing. So, that belongs to a singlet, 1 multiplet of member 1, and spin 1 belongs to multiplet of 3, which is a triplet. In a similar fashion, if you do the algebra and then consider the SU3 grouping, then 3 cross 3 bar is going to give you an 8, a member, a group or a multiplet of 8 members and 1 singlet. This should add up. 3 into 3 is 9, so that is equal to 8 plus 1. Similarly, for the spin case, 2 into 2 is 4 and 3 plus 1 is also equal to 4. Okay. So, now let us take U, D, S, find out what are the different type of mesons you can make with a U bar, a D bar and S bar under the flavor. This tells you that you can have a U bar, you can have a U D bar and you can have a U S bar, you can have a D D bar, you can have a D S bar, you can have an S S bar, you can have D bar U, D U bar, okay, D U bar, and you can have a S U bar and an S T bar. There are 9 such possibilities, of course. So, 9 combinations. Now, how do you make it an 8 and a 1? We saw that U D bar is nothing but a pi plus, and a pi 0 is 1 over root 2 U bar D D bar minus U bar, and pi minus is a U bar D. Okay. So, these are taken up. Actually, then you see that U D bar is taken over, U D bar is taken, let me circle that, and then U bar D is also taken by pi minus. D D bar and a combination of D D bar and U bar is also considered in that. So, there must be another combination of U bar and D D bar, or along with something else which will come up as another one. And you have a K plus which we had considered, which is U S bar, and K 0 was D S bar, and then you had K 0 bar was, or K 0, K minus U bar S, K 0 bar is equal to D bar S. Okay. So, these are already identified, we know this thing. Now, we already have one particle which has electric charge equal to 0, which is one particle pi 0, which is taking up the combination d d bar and u bar. There is one singlet that we have to make as per our split of 3 cross 3 equal to 8 plus 1 using u bar, d bar and ss bar. So, that singlet should be treating u, s and d in a similar fashion. So, let me call that singlet as eta bar and write it as u bar plus d bar plus s bar in a taking it in exactly the same footing compared to each other. Normalization constant is 1 over root 3. So, that eta bar dot product or the normalized eta bar is normalized, the wave function is normalized to 1 over 3 root 3 1. Now, an orthogonal combination of this is given here pi 0. If you look at pi 0 and eta prime, they are orthogonal to each other. Okay. Now, if you take, you have to make one more orthogonal combination and that can be written as, so orthogonal combination which is orthogonal to both eta prime and pi 0 is you have to have a u bar u bar and d bar plus with a plus sign, because that will make sure that it is orthogonal to pi 0. And to make sure that it is orthogonal to ss bar, now that you have to ask the u and d part the same, that will give you a 1 plus 1 which is 2. You have to cancel that by 2 s bar. So, that the whole thing is orthogonal to each other. U bar, that will give you a 1, d bar will give you another 1, and minus 2 ss bar s into 1 ss bar will give you a minus 2. So, that it is orthogonal to the combination eta prime. So, thus we have 9 combinations, right. So, 9 combinations out of u bar, u d s and u bar d bar s bar. And since we have put them in different multiplets, let me collect those things and then put it in a group of 8 and a group of 1. How, and conventionally what is done is you actually put it in a plane of I3 and S, where S is called the strangeness. Okay. So, since we did not make this especially explicitly earlier, strangeness. Similar to the isospin, we will also assign what is called strangeness quantum number. So, the strangeness is assigned so that u quark and d quark has strangeness equal to 0 and s quark has strangeness equal to plus actually minus 1. So, with this we will see that if you put in a plane of I3 and S, the pions are made of u quark and d quark alone. So, strangeness is 0. So, they should be coming in the S equal to 0 plane line, and I3 equal to plus 1, 0 and minus 1. If you take K plus is the quark content of K plus is u s bar, So, the strangeness of this is plus 1 because strange quark has strangeness is equal to minus 1 and S bar, the strange anti-quark, has strangeness equal to plus 1. So, K plus will have a strangeness plus 1 and K 0 will have a strangeness plus 1, and they have isospin, third component of the isospin, equal to plus half and minus half respectively. So, we have K plus and K 0. Okay. And similarly, you have a K minus and K 0 bar with strangeness is equal to minus 1 because the quark content has an S in it. So, they have an S in it. So, let me put a dotted line to join these. So, you have 4 plus 3, 7 members here, and you put the eta which is not a singlet along with it, and this makes a group of 8, and then this is called the meson octet. And the singlet eta prime in the I3 S plane stays alone at I equal to 0, I3 equal to 0, S equal to 0 position, because if you look at eta prime, it has u bar, d bar, strangeness equal to 0, and a term with S bar, again strangeness is 0 there because S quark has strangeness minus 1 and S bar has strangeness plus 1. So, this is how this grouping goes. So, we have a meson octet which we have somehow supported, the why we put it in an octet in some fashion. We have some kind of a support from the quark model, where we can think of the S, U and D quarks belonging to a triplet of SU3, and then similarly for the anti-quarks, and then make a combination of these quark and anti-quark, and then see that they actually can be thought of as a group of 8 and a group of 1. Baryons. We can actually think about the other mesons also in a similar fashion, put them in different groups, multiplets, different multiplets of under the SU2, SU3 grouping. But now coming to the baryons, we will be able, we have they are made of 3 quarks. So, we should be taking under SU3 of flavor, you should be taking a member from a triplet and a member from a triplet and a member, another member from another triplet. Then see that group theoretically this 3 cross 3 cross 3 will go to a 10 and 8 and an 8 and a 1. So, you will have a group of 10, a group of 8, a group of another group of 8 and a singlet. Okay. So, with UDAS grouping, and we can actually work it out in exactly the same way as we have done earlier, and we will see that. So, I will write only the quark contents here, not exactly the wave functions. So, quark content of P, the proton is UUD, and quark content of neutron is UDD. So, again in a plane of I3 and strangeness group. So, they will come at okay, so let me, so this is your I3. So, proton and neutron are spin, isospin half, and I3 equal to plus half for proton, I3 equal to minus half for neutron. Strangeness is equal to 0 for this thing. And then you can actually, you have another set of these baryons which are called sigma baryons. There are 3 different types of them: sigma D, sigma minus, sigma 0, UDS, and sigma plus, which is UUS. All of them has one strange quark in it, and therefore, the strangeness is minus 1. So, strangeness minus 1, isospin half, isospin minus half is isospin 3, third component of isospin minus half is sigma minus, and sigma 0 has isospin 0, and sigma plus has isospin, third component of isospin equal to plus 1. And then there are 2 other baryons which are called cascade 0, which can be thought of as made of a U quark and an S quark SSU, UUSS, and cascade with a charge minus 1 unit, which is DSS. And they have isospin third component plus half, which is cascade 0, and minus 1 unit, which is cascade minus. And along with that, you have another one called with I equal to 0, which is UDS, the lambda quark. So, these things together, okay, so lambda will also come there, can be thought of as a multiplet of 8, okay, and when you put it in a I3S plane, they will be arranged in this fashion. This is called the baryon octet. We indeed have another baryon octet, and the 10 is also there. We will discuss that in the next class.